Hello, everyone, and welcome. My name is Ryan Sokol, and I'm here with our final MAMNA virtual seminar of the fall. And so I'm going to introduce you to our co-host and our co-president, Heidi Leonard. Who do we have today?
Thanks, Ryan. So today we have Xiao Wang. She received her bachelor's in physics from Nanjing Normal University in China and her PhD in physics from Bryn Mawr. And she is currently a postdoc with Professor Xuemei May Cheng at Bryn Mawr. And she's going to give us a lesson on skyrmions and nanomaterials, and let's see what else. So Xiao, the floor is yours. Take it away.
Thank you, Heidi. Thank you, Ryan. Good afternoon, everyone. It's my great pleasure to present my research about magnetic skyrmions in multilayers with interfacial Dzyaloshinskii-Moriya interaction. I conduct this work under the guidance of my advisor, Professor Xuemei May Cheng, and mainly in collaboration with researchers from Argonne National Lab, Colorado State University, and Lawrence Berkeley National Lab. So here is the outline of my talk. After introduction to the magnetic skyrmion, I will talk about sample system and fabrication, as well as the skyrmion imaging methods for us to visualize the magnetic skyrmion. And then I will present our interesting results about the skyrmion Hall effect, which we observed during the current-driven skyrmion motion. Finally, I will summarize. So, why researchers are so interested in magnetic skyrmion? Let's first have a quick review of the history. So in 1980s, two experimentalists, Alberford and Peter Grunberg, discovered a giant magnetoresistance, shorted for GMR, in which the magnetoresistance has a giant difference between the anti-parallel magnetizations and the parallel magnetizations, showing us here, and which opens a new era of spintronics. So different from the conventional semiconductor devices, spintronics aims to utilize the coupling between spins and electrons to develop the next generation data storage devices. And as one example of the application of GMR, in 2008, Dr. Parkin proposed the concept of a domain wall racetrack memory, as shown in the cartoon. So driven by a current, the domain walls, which is the boundary of these blue and white areas with anti-parallel magnetizations, pass through this GMR sensor, resulting a changing in the voltage. More specifically, so when the blue area passes it's a parallel magnetization, but when the boundary between blue and the red passes anti-parallel magnetization, therefore the difference in the resistance resulting in the changing of the voltage. And however, this device requires a high current density, and the domain wall pinning effect makes it impractical for the real application. So in 2013, the same Alberford, 2007 Nobel Prize winner, proposed the magnetic skyrmion as a new way for this data storage, for this non-volatile information storage with ultra high density, ultra fast speed, and ultra low energy consumption, because the magnetic skyrmions can not only wind around defects to avoid the pinning effect, but also requires a current density as low as 2 orders of magnitude smaller than what is required for this domain wall racetrack memory. So later, our collaborator, Dr. Wang Zhang, has demonstrated the possibility of skyrmion-based racetrack memory, showing us here. So now, what are magnetic skyrmions, and what makes magnetic skyrmions such promising candidates for the next generation storage? So magnetic skyrmions are actually topologically protected chiral spin textures, and they behave like particles. So here shows an example of a nail-type skyrmion. So as you can see, it is a circular symmetric spin texture. If we look at the cross section along the radial direction, the spin at the center points up and it gradually translates to the edge where the spin points down through a particular transition that is the same as the nail-type domain wall structure. Therefore, we call this type of skyrmion nail-type skyrmion. And now, so with this example, we can inspect the characteristic features of magnetic skyrmions in a less abstract way. So here, behave like particles. It's easy to understand behave like particles. So although many spins formed a magnetic skyrmion, but they act as a group, making magnetic skyrmion a particle-like thing. And I think that's why physicist Tony Skyrm just named these things as skyrms, particles, skyrmion. And the second thing, chiral spin texture. I just means that if you, okay. So the chiral just means that if we take a random radius direction and one side of and the other side of the skyrmion has which can are like our left and right hand, which cannot be superimposed. And the last part is this topologically protected, protected, which is actually the most important feature. It originates from the mathematical concept topology, which describe the geometry of features and the stability of things related to the geometries. So Tony Skyrm actually was a nuclear physicist. He borrowed this topology concept into the nuclear physics to explain certain particles are more stable than the other particles. For example, neutrinos, neutrons are more stable. And so he thinks those stable particles can be explained by the topologically protected nonlinear vector fields, and they can characterized by integer topological numbers such as the -1, 0, 1, all those. So later, physicists borrowed this topological protection concept introduced by nuclear physicist Tony Skyrm into the spintronics to describe certain magnetic configurations with the certain topological protected features as magnetic skyrmions. And the property of the topology can be described by a topological number or topological chart, which is the integration of the magnetization of the whole matter. And as you can see, the integration is the third order of the magnetization of each spin. So if we change the direction of each spin to its opposite direction, and then we'll get a magnetic skyrmion with the opposite topological charge. Here is -1. So the topological magnetic, therefore this magnetic skyrmions are not only have great those magnetic skyrmion not only has great potential in the technology application, but also concerns the fundamental condensed matter physics phenomena such as topologies. And as you may know, 2016 Nobel Prize was awarded for the theoretical discovery of topological phase transitions and topological phases of matter. So Then, so if so with skyrmions, with those interesting magnetic skyrmions, how do we realize magnetic skyrmions in our sample in reality? So it is related to the nanomagnetism. So we know the magnetic configurations are the stable state with energy minimization. And the energies that related to, it's like a apple always fall into the ground. That's the minimization of the gravity energy. And for magnetic configurations to be stable, it requires a minimum energy minimization of the magnetic energy. And it involves the Heisenberg exchange energy, dipolar, Zeeman anisotropy. And the Heisenberg exchange tends to align the adjacent spin either parallel or anti-parallel. And dipolar interaction tends to form a closed fluxure. The Zeeman tends to align the magnetic spins in a sample to the external magnetic field direction. And the anisotropy just means there is a certain direction that is more preferred for the magnetization in the sample. And the last, the Dzyaloshinskii-Moriya interaction is the key in skyrmion stabilization. So what is Dzyaloshinskii-Moriya interaction, DMI? It is actually an indirect and asymmetric exchange interaction that requires strong spin orbital coupling of a heavy metal and a broken inversion symmetry. It can be described as a dot product of Si and of the dot product of D vector is Dzyaloshinskii-Moriya parameter, and the cross product of two adjacent spin. As you can, so mathematically, as you can see, to minimize this DM interaction, we will we want a negative maximum number, right? And so therefore we require this D to be perpendicular to be this has to be perpendicular to the cross product of Si and Sj. And for the Si and Sj to be maximum, it's better for them to be perpendicular to each other. So Si, okay, sorry. So D is the same direction, no, in the opposite direction of cross product of Si and Sj. So then we will have a negative D magnitude and this magnitude. And this for Si and Sj to be magnetized, and they will be perpendicular to each other. So you have sine alpha equals 90, and which this is the key part for us to form this rotation spin configuration, because for all the other interactions, for example, Heisenberg exchange, they either tend to align spin parallel or anti-parallel. It doesn't have like this rotation and the gradual changing of this spins. As you can, it's easy to tell if we change the direction of the D factor, the rotation direction of the spin will also be changed. And therefore, here shows the example of the interfacial Dzyaloshinskii DM interaction at the interface of a non-magnetic material and a magnetic layer. And with the DMI phase interaction pointing along the in-plane direction, and we can form the spins rotating perpendicular to the interface and forming this Snell-type skyrmion. And so now we know what the mechanism for the skyrmion to be stabilized, and then we want to come up with a system that matches all the requirements. So we need the interfacial DM interaction to we need the interfacial DM interaction in the system and the perpendicular magnetic anisotropy. So in our system, we have this sandwich structure of the ferromagnetic cobalt iron boron and the heavy metal tantalum and the insulator tantalum oxide, which has a broken inversion symmetry at the two boundaries of a ferromagnetic layer, and with the induced interfacial DMI at the interface. And we also see the weak perpendicular magnetic anisotropy in this system. So we deposit our film using the magnetron sputtering. And so in order for us to do the current-driven experiment, we need to pattern the film into devices so we can have the electrodes and then be wire bonded to send current through the film to drive the potential skyrmions. Therefore, we pattern the films with photolithography with laser writer. Now, with our samples, we need to image the potential skyrmion to see how they react when driven by a current. We know we can see a magnetic bar, but we cannot see the magnetic flux or magnetic field with the bar. Therefore, we need we use some iron particle or freckles to interact with the magnetic field to illustrate how the magnetic field is. It's the same with other magnetic imaging methods. They have different mechanism to interact with the formed magnetization configuration in the sample to indirectly illustrate those magnetic configuration. And I used magneto-optical Kerr effect microscopy, photoemission electron microscopy, and Lorentz transmission electron microscopy for my research. They have different aspective of advantages. Some have higher resolution, but some are more user friendly with more freedom in sample environment. For example, we used this magneto-optical Kerr effect to image for the current-driven experiment, because we can easily apply field and send current pulses with just putting the sample down here for it's basically a microscope with a polarizer and analyzer. Okay, so now we know the methods, the sample system, and everything. Let's see some results. Upon apply current, we can see a few skyrmions were formed in the device, and instead of moving along the current direction, they actually have a more linear kind of trajectory, but forming an angle with the direction of the current. And if we make the devices even narrower, we can see that for skyrmions actually accumulated at different skyrmions with different opposite topological charge actually accumulate at opposite sides of the devices after a certain amount of time. And all those things actually just resembles the charge behavior, electron behavior we observed in the Hall effect. Like in Hall effect, the electrons go towards to the edge instead of moving along the current. So yeah, so here we compare the ordinary. So the well-known Hall effect, we here call it ordinary Hall effect, just describe the transverse deflection of the electrons of the charged particles as a result of the Lorentz force. And our skyrmion with the topological charge, instead of electric charge, also moves towards the edge of the devices and form an angle between the motion trajectory and the current direction. So therefore, this phenomenon is so named as the Skyrmion Hall effect because it's analogous to the ordinary Hall effect. But here's the question. So in ordinary Hall effect, it's a Lorentz force that plays a role behind this deflection trajectory. But what's the force in our magnetic in our Skyrmion Hall effect? So let's so let's first borrow this idea from the soccer ball, and here shows a famous Brazilian expert, soccer ball expert, Roberto Carlos' famous banana kick. And you can see for his kick, instead of moving directly, it has a trajectory that winds around the French players and then aims into the goal. So most of you probably already know the tricks behind this magic kick. It's the Magnus force. So in the reference frame of this rotating ball, because he gives a side kick, so this ball was spinning while moving towards the goal, and because the spinning motion of this soccer ball, the air is accelerated on the right side and deaccelerated. So this blue arrow indicates the moving direction of the ball, and this is spinning direction. So here, the spinning direction is the same as the moving. So the air at the right side is accelerated, while the air at the left side is deaccelerated. Therefore, the air flows bend towards the left. According to the Newton's third law, as the air experienced the force towards the left, the ball experienced the opposite force, the Magnus force, towards the right. And when a magnetic skyrmion is driven by the current, the emergent magnetic field on both sides has a different sense of rotation. The net effort of this Lorentz force on the conducting electron deflects the current to the left, and in turn leads to the counter effect, the magnet force on the magnetic texture pointing to the right. Therefore, without us even spinning the skyrmions, the unique chiral spin texture of a magnetic skyrmion can introduce this rotating effect and giving us a magnet force that towards the side, that is like towards the side instead of moving along the current direction. So with the theory background, then we systematically investigated the Skyrmion Hall effect with different amplitude of current. And we can see with an example of 2.8 ampere per centimeter square current, for topological for skyrmion with opposite topological charge, they have a different skyrmion motion trajectory. One is towards the up and one is towards the downside of the edge. However, if we decrease the field, decrease the current density, you can see this obvious linear motion trajectory is got changed, and they move quite like a hopping motion. So this is the hopping regime of the skyrmion motion. So to fully inspect and the field dependence and the current dependence and topological charge dependence of this Skyrmion Hall effect, we made this diagram as showing here. And you can see that with small current, there is no Skyrmion Hall effect. But as the current density increases, there is a linear increase of this Skyrmion Hall angle, and at a certain magnitude of the field, this trajectory kind of saturates with the maximum Skyrmion Hall angle. And also, the Skyrmion Hall angle is related to the size of the Skyrmion. And the topological charge of the Skyrmion. So in summary, magnetic Skyrmions are promising candidates for future data storage, and multilayers with interfacial DM interaction are promising systems in realizing nano-type Skyrmion. Interfacial DMI is a key in the formation of nano-type Skyrmion, and the Skyrmion Hall effect was observed by the MOC imaging, and we summarized the topological magnet first and made the phase diagram for the Skyrmion Hall angle, and in the end, I would like to thank my advisor, Professor Xuemei May Cheng, for supervising my research and all my collaborators. Thank you, and thank you for listening.
So thank you, Xiao. We have a couple questions for you.
Sure.
So the first one is from past President Brendan. He says, excellent talk. I see you are fabricating by sputtering. I'm assuming all 3 layers are grown without breaking vacuum. Can you comment on how important those interfaces are?
How important the interfaces do not need to be perfect, but they like we said, the interface, because we need the interface because we need the interfacial DM interaction, and which only exists at a broken inversion symmetry. And with the interface of a ferromagnetic and a non-ferromagnetic layer. So as long as you have those materials, and it does not need to be perfectly like the roughness. We think it has a large tolerance of the roughness of the sample.
And Brendan also asks, what is the Skyrmion velocity and how does it scale with current density?
Oh, the velocity actually probably the velocity it's so for a 10 to the 6 ampere per centimeter for this scale magnitude of current density, the velocity is less than 1 meter per second.
Okay. And now my question is so were you trained on all of those imaging instruments that you used?
Yes, yeah. I did. I mainly did MOC and PIM. So PIM is like in the synchrotron. It's a synchrotron related. It's like a XMCD PIM. It's in the Lawrence Berkeley National Lab LS Advanced Light Source. So we just write proposal and we go there, and the beamline scientists help us setting up the a measurement, and then we just collect the data ourselves.
Wow. And then did you TEM as well?
Yes, the Lawrence TEM is a facility at Argonne National Lab, but it's owned by Dr. Dr. DJ there. That's their group property. So they do have a postdoc who is in charge of this instrument, but we like collaborate. We kind of like just bring the sample and do the measurement together.
Got it.
And yeah, and this MOOC is I basically just 24 out of 24/7. It's mine when I was at Argonne.
Nice. So Brendan also asked, is that velocity going to be a challenge for electronic applications in reference to the Skyrmion velocity?
Yes, this is actually another thing we are working on. So theoretically we found that for the anti-ferromagnetically coupled skyrmion, so we have skyrmions with topological equals -1 and +1 and -1, right? So now we found if we couple these two skyrmions together, and then we'll have an anti-ferromagnetic skyrmion, which is insensitive to the stray field and does not react to any so it has a lot faster mobility than the ferromagnetic skyrmion. So this is our next step towards making this more practical in application. Yeah, and also this also helps us to cancel the Skyrmion Hall effect, because we do not want the Skyrmion Hall effect in the racetrack memory, right? We do not want it to move towards the edge where there will a lot of defects. Oh, and actually, I can show here. So yeah, so for in the internal of the device, you can see it moves along a line, but at the edge, you can see they're kind of like having this hopping motion because the edge repulsing force and the magnet force. So we do not then want them to move close to the edge. Therefore, we come up with this anti-magnetic coupled skyrmion, which then will have a total topological charge of 0. So we do not have this like a motion towards the edge. And yeah, then that will also have faster mobility compared to the ferromagnetic skyrmion.
Yeah. Another question is from Tony Milla Robles, who says, nice talk. My question is, what happens if instead of nail type skyrmions, we use another type of magnetic skyrmions, maybe block type skyrmion or anti-skyrmion?
Yeah, I think it's yeah, I think we experimentally discovered block skyrmion first, but the disadvantage of block skyrmion, but the advantage of nail type skyrmion comparing to block skyrmion is that block skyrmion tends to exist in bulk material, and they need a larger, very large, up to Tesla magnetic field to stabilize, and very low temperature. But for nail type skyrmion, they can be stabilized. We have already stabilized nail type skyrmion at room temperature and without external magnetic field. And another advantage of nail type skyrmion is it exists in those kind of multi-layer systems. So you just need sputtering to fabricate this multi-layer. For bulk material, it's harder in sample fabrication comparing to magnetic multi-layers in my perspective. Yeah.
Well, I think that's all of the questions, but thank you so much for your talk. I think that was pretty different from the rest of the talks we've had recently, which were mostly biomaterials related. So it's nice to see something different. But yeah, thank you, Xiao. And that concludes our fall seminar series for MAMNA. So we'll keep you posted on what's happening next.
Okay, thank you.